TPOS 20, so this is Tropical Pacific Observing System 2020. It began as a response to a series of crises in the observing system in the tropical Pacific. And they had different reasons, but basically, organizationally, it's very difficult to maintain projects for the long term, especially ones that require partners that have different interests, different mandates, different constraints to cooperate over the long term. And so we don't need to go into this, but there were problems first in the Tau array that extends across. Well, actually, I can use this map. Okay, so you recognize here Mexico, Central America, Australia, New Guinea, and all of these squares are moorings that measure they have a surface buoy that measures the surface meteorology, the winds, the humidity, the air temperature, and then they have a subsurface part that measures the temperature, the salinity, and sometimes the velocity. And there, I believe, 77 of these altogether. This part has been done by the United States, and this part has been done by Japan. And anyway, there were problems that led to a loss of data. Now Japan is withdrawing from this part in the Western Pacific. And so in response to those crises, we formed this project called TPOS 2020 to rethink these arrays. Okay. And so I just have a few slides on TPOS 2020. So I would say the fundamental idea that we're working on is that different platforms, that is satellites, moorings, Argo floats, gliders, we have many different ways of observing the ocean, have complementary strengths. And the three mature technologies that we call our backbone are complementary. So satellites in general give global coverage. They give fine spatial detail in the horizontal direction. Moorings, by contrast, sample a wide band of frequencies. So that means you can do spectral analyses, you can understand the fine temporal scale phenomena that often are important for the larger scale. Moorings also give you co-located ocean atmosphere observations, and it's the only way we can measure velocity directly in the ocean. The Argo floats, do people know Argo floats? Yeah, okay, good. So that is also global. It resolves the fine vertical structure, and it gives salinity. And one way to think of these is that satellites give you good detail in X and Y. Moorings give you good detail in time, and Argo gives you good detail in the vertical direction. So each of these fills weaknesses of each of the others, and the integration of these three pieces, that's fundamental to how we think about the new system. So in the past, all three of these have been done essentially independently and by different groups without thinking about how the pieces fit together. And what we're doing in TPOS 2020 is trying to put those pieces together. Now, in order to really get the value out of that, you need a system of data assimilation that takes these diverse kinds of data that have very different characteristics and merges those into a consistent whole. Now, that should add value. And eventually we'll get there. Certainly in the atmosphere, that's how it's done. But in the ocean, that is not yet the case. So we're in a kind of a middle ground where we can see where we're going, but the models and the data assimilation systems are not ready. Okay, and so we've envisioned an eventual in situ backbone system, and by eventual I mean in something like 5 to 10 years. And the red squares here show the historical Tau Triton mooring sites. So 95 West, you probably know, 110 West, all the way over to that's the Tau Triton array. And the way we envision changing that is that green indicates moorings, in many cases denser moorings. Moorings line extended from 8 North across the ITCZ in the east and the west, and across the SPCZ in the west. And the blue areas show where we picture fewer moorings but more Argo floats. Now, this map is very fuzzy, and it's fuzzy because there are many things that we still don't know about what we need. So one more slide about TPOS, and that will introduce the pump program. So we really intend to advance, not just to maintain what we're doing, not just to do it more efficiently, but to really advance. And to do that, we recognize that there are many pieces where we don't know enough to advance. So in our first report that is about to, the business of the meeting next week, is to finalize this first report. And we recommend a variety of process and pilot studies. I'm not going to talk about all of these, not at all. But these are areas where we think we need more knowledge in order to take that map and make it less fuzzy. And the one I'm going to talk about today, the rest of the talk, will be about the pump process study. I know you can't read this, but we'll talk about that in more detail. But this is just one of several process studies that we're recommending. So pump, it's a process study to look at the whole complex of mechanisms that connect the thermocline to the surface in the equatorial Pacific cold tongue. So in brief, we know that there's upwelling, there has to be mixing down, there's strong gradients of currents, there's strong solar radiation. There's the whole complex of processes that are now relatively unknown. And we have two premises. That is to say, why do we think this is something we're ready to do? And one is that the ocean models are ready to exploit realistic vertical exchange processes, realistic mixing, but they don't have the observational guidance that would let those parameterizations develop. And we now have new understanding of mixing from sparse observations that now let us propose specific hypotheses. So why is this needed? And there's two real reasons. The first is, and we all know that ENSO is not a solved problem. And we've seen, especially over the past 15 years, that we have very limited ability to make a confident forecast of El Nino. And that's a big problem for society. And we need to make progress on that. And we think that the upwelling and the resulting air-sea interaction, right? So you get upwelling, you get cooler water, the atmosphere on the equator responds very quickly to that, and so then the winds change and the upwelling changes, and that whole set of ocean atmosphere processes are fundamental to El Nino. And this is the part we don't know. It's just what's happening on the equator when the winds change and the upwelling changes and you have these coupled feedbacks. And second, the equatorial Pacific has global significance. So I think I just said this, the powerful air-sea coupling of the equatorial Pacific doesn't just affect the Pacific, but that reverberates through the entire global climate. And so if you ask, what is it about the tropical Pacific that someone in Europe should care about, or someone in Africa, or someone who's not in the tropical Pacific, it is really fundamentally comes down to this coupled upwelling, mixing, and air-sea interaction on the equator. So there's a lot of pieces of the tropical Pacific climate that are relevant regionally, and Ken might disagree with me, but I'm going to give an example of the upwelling along the coast of Peru. Okay, so that is clearly very important regionally. It also is part of the general circulation of the Pacific because you have upwelling from below the thermocline. It's one of two places in the Pacific where subthermocline water comes up. The other is the Costa Rica Dome in the north. And so coastal upwelling here is a very important process for the Pacific circulation. But if you're not in the tropical Pacific, the one that really matters is this upwelling, equatorial upwelling. And so as TPOS 2020, we must get this right. Okay. So I'll talk a little bit about what the circulation looks like in our present ocean general circulation models. So this is a slice from 10 south to 10 north, from the surface to 250 meters. The colors show the zonal current. So this is the equatorial undercurrent here in red, the south equatorial current in blue, a very weak north equatorial countercurrent in red. And the vectors show the meridional circulation, that is the upwelling and then the Expone divergence. So we know that these strong currents that are flowing away from the equator on both sides are because the trade winds are blowing to the west. The Expone transport is outward from the equator, and we get this powerful divergence on the equator that generates this strong upwelling in the center. So that's the way we see this from a present model, and we know that that general picture is correct. Now, however, when you look at different models, or even when you take the same model and change the resolution or change something fairly small about it, you find that you get very different pictures of the meridional circulation. And I don't know if you can see these thin lines here. Those are the zonal currents. So I'm just going to go back. We have the equatorial undercurrent here. So this is strong positive current at about 100, 125 meters. Whoops. 100. Whoops, wrong way. About maybe between 100 and 150 meters, strong zonal current. So in these very light lines here, you see U. So this is the equatorial undercurrent, this positive bulge at about 100 meters or so. And these are two models. So one is a fairly early version of MOM2 at 1/3 of a degree, and the other is a model from NCAR at 1/10 of a degree. And what these model developers have been able to do is to tune the models to get the undercurrent right. And we know they get that right because the velocity is measured directly on the equator. And we've been doing that for 20 years now. And so they can tune the model to get that right. And you can see that these two agree fairly closely. And I didn't put the observed on here, but it would be that same picture. So the models are able to get the zonal current right. But now look at the vertical. So this is W now. These two lines are W. So the same two models, completely different pictures of what the vertical velocity is like. So the usual kind of comparison, the one we're able to do with observations, comparing the equatorial vertical profile of the zonal current, the models do that very well, but they are essentially unconstrained in the meridional current. So, and this is just another example of the variability of temperature along the equator, same two models. This is essentially what the observed temperature variability looks like. Sorry, this poor quality here. This is the vertical, and this is the zonal direction, and this is the RMS temperature along the equator from this is essentially the observations, very large. The two models much weaker and also very different. And what that says is it's possible, So let's consider an easterly wind anomaly on the equator. So that's going to give cooling because of latent heat fluxes, that is more evaporation. It's going to give cooling because the increased wind speed will increase the mixing, and it will give upwelling because of the Expone divergence. Now all of those things will be in phase. So you can tune your model to get the right zonal current, to get the right SST even, and even the SST variability. And you might be doing that for the completely wrong reason. Maybe your model has very strong mixing but too weak upwelling. But you would not be able to tell given the observations that we have now. And so it's possible to get the right phase of anomalies, even the right amplitude of anomalies, for a completely wrong reason. So that's another reason why we need this kind of process study. So the picture now that we're looking at in pumps, so this is obviously a cartoon from 5 south to 5 north. This is the equatorial undercurrent, so say this is from 100 to 150 meters, something like that. The blue shows current velocity, so the equatorial undercurrent is to the east. The south equatorial current above it is to the west. Here's the Ekman divergence. Here's the red is the solar radiation. And these little round things are supposed to indicate mixing. Now we know that the upwelling implies that you have strong mixing. And the reason that must be the case is because this upwelling is on the order of several meters a day. Okay, that is pushing everything up at 2-3 meters a day. But we do not see the isotherms moving up. We see them basically stationary. They're varying, but overall they remain stationary. And that means that some combination of this solar radiation and this mixing must be balancing the upwelling. So that's kind of what's happening. In the mean, anyway, the solar radiation and the mixing is balancing the upwelling, and all of those things must be very strong, because this upwelling, 3 meters a day, that is, if something wasn't balancing it, you would see very large changes. So maybe I put this out of order, but I'll talk about it anyway. So one of the ways that we tell that the mixing in the models is not adequately constrained is by comparing the strength of the thermocline. So this is showing n squared, so an index of thermocline strength at the equator 140 west. The black line is the observations, the red line is a GFDL MOM3, and the black line is, the blue line is the observations. The black line is the NCAR POP model. So the observed thermocline is much sharper than either of these two models. And there are many ways to see that the model thermoclines are too weak, and that actually matters. And this comes from a study by Jerry Meal in 2001. I'm going to have to come over here to read it. So this is a plot showing, so these are from many model runs, are the dots here, and the shaded line is roughly the observed range as a function of background vertical diffusivity in the model and the standard deviation of Nino 3 SST. And so the observations are, doesn't have vertical diffusivity, so it's just a band. And what Meal found, and it's worth really paying attention to it, the dominant influence on El Nino amplitude is the magnitude of the ocean model background vertical diffusivity. That's this. Across all model experiments, regardless of resolution or ocean physics, the runs with the lowest value of background vertical diffusivity have the largest Nino 3 amplitudes. And that's because a lower diffusivity gives a shallower and sharper thermocline. The model is more sensitive to coupling with the atmosphere. You get larger amplitude of ENSO. So this, now again, we're talking about, we need to know the mixing. That's one piece, and we need to know the upwelling is the other piece. And we have some ability to measure upwelling if you average over the entire cold tongue. And so this is an average from 5 south to 5 north, from 90 west to 170 west, the entire cold tongue region. And Meinen and McFadden and Johnson were able to make estimates of the vertical transport. And this is where my number of 2 to 3 meters per day comes in. And it's worth noting that the black line, which is the total vertical transport, is different from the cross isotherm component. And that's because the equatorial undercurrent and thermocline is sloping up to the east. So if you're just measuring W at a point, if you could, they would show a component of W that was just due to the undercurrent flowing up that slope. The cross isotherm component is different. I should have put a 0 line on here. The cross isotherm vertical velocity, so this is the part that has to be balanced by mixing, is higher in the water column. But remember, in order to do that, we have to make a very large space and time average. And that's basically by balancing the transport. Sorry, I'll go back to that. the way they did this is to measure the depth of 20 degrees C isotherm, so that's essentially the thermocline, or maybe they did several isotherms. And the geostrophic flow out 5 south and 5 north, and the measured equatorial flow at the east and the west end, and that tells you what the total vertical transport through that isotherm has to be. Okay, now let's talk a little bit more about mixing. And actually, I think, well, no, I'll talk about this first. So this is a plot of dissipation rate. It's essentially a measure of the amplitude of mixing. Red shows high mixing. This is 10 days here. And what you see is that every afternoon and into the evening, you have this plume of high mixing that's extending down to at least 80 meters, basically down to the top of the thermocline. And I'll talk in a minute about why that happens. But what this shows is that the mixing ends up, mixing generated at the surface is transmitted all the way down to the top of the thermocline. Now, there are very few estimates of this. This was a 10-day intensive experiment. And when you collect all of the eddy diffusivity profiles in the cold tongue, you get these three. That's all there is. And they differ by orders of magnitude. So we really don't understand how the mixing, even how it depends on whether you're in an El Nino, what part of the seasonal cycle you're in, anything about the background. And the reason, one mechanism by which you get this mixing that propagates down occurs through the diurnal cycle. So this is now from the surface to 25 meters and during a composite day. So this is local time 0 to 24. The colors show the temperatures and the colors show the temperatures. And what you see is you get an afternoon warm layer that's very shallow, 5 to 10 meters deep. Very strong stratification at the base of that layer. Whereas at night and early in the morning, you have no stratification, that temperature is quite uniform. And notice that these contours are very fine. The top vectors show the wind. Again, a composite diurnal cycle, and there's very little diurnal cycle of the wind at this location. So despite the fact that the wind is almost constant during the day, you get this afternoon warm layer. And what that does is it stratifies, and it creates a layer that traps the wind input momentum in a shallow layer. And so the vectors that you see in the ocean here are the shear relative to 25 meters. And what you see then is that the afternoon warm layer traps the momentum. You see these vectors get both larger and more closely in the direction of the wind in the afternoon. So whereas you have relatively little shear in the night and early in the morning, now you have a very strong shear. I think this is 12 centimeters a second between 25 meters and the 5 meters. That shear overcomes the stratification, right? You get a low Richardson number here, strong mixing. That layer moves itself down. And now, and it keeps doing that through the evening. So now here you are at 8 o'clock in the evening, and you can see how this thing has propagated itself down each time by trapping momentum, generating shear at the base of that layer, causing mixing in that layer, and the layer mixes down. And that takes time, and that's not a wave time scale, but a physical mixing time scale. And it means that you have a time lag of something like 4 or 5 hours between the surface maximum heating and when it gets to 25 meters. And so that is what you're seeing. This is the previous slide here now. So this is a direct measure of mixing. You see how these things are all sloped down. It goes below 25 meters down to the top of the thermocline. And we think that this mechanism is a primary way by which the ocean feels the surface fluxes. You know, we have a picture of the wind blows on the ocean and the thermocline responds to that. And when you ask, how does that really happen? then we have very simple kind of models or theoretical models, schematic models that say, well, the ocean has a constant shear mixed layer, or it's a slab mixed layer. We have many different ideas about that. But what this is arguing is that the diurnal cycle is really a key piece of how the surface momentum and heat fluxes are transmitted down. And you can see that here. There are very few observations of this, but there are 3 of them, actually. They all show this same kind of thing. A time lag between the surface and the subsurface based on this afternoon warm layer, shear trapping, shear building up, overcoming that stratification, and moving itself downward. Okay. I think that's almost the end. Maybe it is the end. Okay, so back in 2005, a group of us proposed a moored array that would study this problem. And I don't even know how relevant this is now. I believe there were 17 moorings proposed. It would be a gigantic... Ken is just laughing. He says, how are you possibly going to do that? Well, I don't know. But I think this is the kind of thing you would need to do. And the idea is that these moorings are measuring velocity. You would now be able to get velocity and velocity derivatives. And remember, we must have the velocity derivatives to get the vertical velocity, right? Basically, it's dv dy is going to give you w. And anyway, we proposed this. It didn't go anywhere, and now it seems like it's coming up again. So this is my last slide. The goals of a redone pump study: to observe and understand 3 things. The evolution of the equatorial cell under varying winds. So that means, it's one thing to talk about the mean. It's another thing to talk about mechanisms that are part of the mean, like the diurnal cycle. But what I think we need to be able to do is to understand when the wind changes, either increasing or decreasing, how does the upwelling respond? How does the mixing respond? How does that balance between upward motion, downward mixing change when the wind changes? And right now, I showed you that our models, they're basically unconstrained. There's no idea what reality actually is, and the models are then able to produce quite different solutions given the exact same forcing. So to do that, we need to determine the mixing mechanisms. Okay, let's see. So we have mixing mechanisms that determine the depth that wind input, the momentum input by the wind is transmitted downward. The diurnal cycle is a strong candidate for how that happens, and also the surface heat fluxes into the upper thermocline. And 3, we know that there's a sharp SST front north of the cold tongue. I didn't talk about that, but that is an important player in these dynamics. And the result that we want from a limited term process study will be to teach the models to infer upwelling from sparse sustained observations. And the analogy that I would use in the atmosphere, so meteorologists don't observe fronts. They don't go out. I mean, so in mid-latitudes, all of our weather comes from fronts that are traveling along the jet stream, and meteorologists don't, and the atmospheric community is not even trying to observe those. They've developed the models to the point where they observe the environment and let the model generate the front. Okay, and that is the kind of thing that we're aiming for as a result of this study. It's too expensive to think that we would be measuring upwelling all the time on a sustained basis. I don't think that's realistic. But what we do need to do is teach the models so that they can take broad-scale observations that we can do all the time, and then through the model dynamics correctly infer upwelling from these sparse sustained observations. And that's really the goal of a process study like PUMP. Okay, thank you.